Let's calculate gravity on this spinning space station. Okay, first off, what are we looking at here?
Yeah.
So the space station is spinning. This is a particular shot where we're sitting on the space station watching the stars rotate. And I'm going to follow our particular star, this one right here, and we're going to watch it go through a quarter rotation and figure out how long that takes. And this is going to give us how fast the space station is spinning. Okay, so when this star right here crosses the vertical line, we're going to start the timer. And that's going to march its way over here. And when it crosses the horizontal, we're going to stop the timer.
Sounds good.
So here, crossed, starts timer. It's going.
Okay, it's moving.
There it is, right there.
Okay.
Okay, still going.
Coming along.
There it is. Almost. Bam. Okay, so 15 seconds. It went through a quarter revolution.
Okay.
All right, and there is a little bit of stretching here. It's not a perfect circle because the camera's zooming out.
Yeah, okay, yeah. If you're zooming out, it's going to change the length of the circle.
Right. So there's some bending going on. If we keep going, you can see this is inside the space station, and here's the craft coming to line up with the center of rotation, which it does.
Cool.
It's pretty cool.
Okay, so the stars are staying still. They're super far away. They're staying still. So the spinning is because the space station that we're on is spinning. And you said that in a quarter rotation, it took 15 seconds. So it's 1 rotation per minute.
Exactly. So I calculated the spin rate. So we know if it's 15 seconds per revolution, it's going to be 1 revolution per minute. Easy. But we need that in radians per second. So that would be
revolutions.
Yeah, don't work. Only for intuitive gut checks.
Okay.
So the spin rate, which is in radians per second, which is the change in radians divided by the change in time. Pi over 2 radians for 15 seconds gives us this.
Okay, yeah.
Okay. All right. So the next step is we've got to figure out how big the space station is. Okay. So what I did is I figured out, so we have a human scale here. Yep. We have a size of a floor on this human scale. And then I looked at the space station picture, and I saw there's 1 floor.
There's 2 windows of lights. Okay.
And there's 3 floors, about 3 floors. And I'm saying these row of lights is 1 floor. Second row of lights, 2 floors. And then there's no lights here, but it's about the same size, 3 floors.
That's about okay. I'm with you. And then how tall is a floor?
So how tall is a floor? So for 1 level, I looked at, this is a person, this is a man.
Yeah.
And I said there's probably some floor space, and then the space where people walk, and then a little bit of floor space.
Like a drop ceiling with all the electrical goes. Okay, I'm with you.
Yeah. So I'm saying, if I'm looking at this picture, maybe it's 1.5 from bottom to top of the height of him. Okay.
Kind of reasonable, yeah.
So I said the height of 1 level is 1.5 times the height of a man.
Okay.
And I looked at the average height of a man, 175 centimeters. Sure. So 1.5 times that is 2.6 meters. Okay.
So that's the height of a level, sure.
And so then the height, if I go over to this picture, which is dead on, which this red line here should be about 3 levels.
Okay, yeah, I agree.
Okay. So if 1 level is 2.6, I multiply it by 3 to get the total size of this red line.
Section. Of that red line. Okay, yeah, I'm with you.
Yep.
3 times 2.6, whatever it is.
Exactly. And what we need is the radius. I did a diameter so that we can stack a bunch of these together. I'll show you what I mean here. So I stacked. This is the height that we know.
Okay.
And then this is the diameter.
Right.
I dropped it perpendicular. So you just got to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
And some
0.6.
Okay, yeah.
0.6.
Sure,
0.6.
Yeah.
Okay.
Yeah.
So to get the radius, I take the diameter and divide it by 2. So I got 11.6 of the red lines.
Sections.
Exactly. Times 3 times the height of 1 level.
Yep.
Okay, divided by 2. So
divided by 2, that's the radius.
Yeah. 11.6 divided by 2 is 5.8 times 3 times 2.625, which I got from the previous calculation, gives me about 45 meters. So the radius, which would be the distance from the outer here to the inner here,
Yep.
is 45 meters. So 90
Okay,
meters in
sure.
diameter. Actually kind of
Okay.
small.
Kind of small, but also I don't know what a space station would be. Sure. So if that's what you got, that's what you got.
Right. So now we're ready to calculate the centripetal acceleration or the equivalent G.
Sounds good.
Okay. So we know that centripetal acceleration is v squared over r from your physics textbooks.
That's the tangential velocity divided by the radius.
Yep.
Okay, sounds good.
And there's a formula that the tangential speed is the angular speed times the radius.
So if I
Okay.
have a fixed angular speed but a larger radius, then the velocity goes faster. Okay. Yeah.
Yep.
Yeah.
So I plug that in, cross out the r's, and I get omega squared r, which is also a formula. I could have started here. Oh well.
Now let's
Okay.
derive it.
Yep. Okay, so I plug in my numbers. I've got the angular speed in radians per second, and then I've got the radius. Multiply those together, and I get 0.5 meters per second squared, which is pretty low.
That's soft. That's super soft.
Super soft, right? So that's 0.05 of an Earth G. So you're going to be bouncy in this.
Maybe that's why in the movie they say that your socks explicitly have like grip texture.
That's right. But I think this space station is designed so you don't need that. I think they're wearing like business shoes. Is that right?
Yeah, they're wearing dress shoes. That's a good
Wearing
point.
dress shoes. And I think you would design this to be maybe 0.5, maybe close to 1 Gs, like something comfortable, right?
Oh, yeah. In fact, that's a good point because if you are too far away from Earth G, then the human body doesn't maintain its musculature, doesn't maintain its bone density. So for the human factor, you want it to be close to Earth.
I think so. So, which means I think this calculation is wrong somehow.
Oh, okay.
And my guess is, so I don't think I messed up the rotation because we got that directly.
Yep.
And it's being 15 seconds perfectly for one rotation. That seems too good to be true, which means it was designed that way.
Oh, I see
So
what
I'm
you're saying.
guessing, yeah, like 1 revolution per minute. Let's just stick with 1 revolution per minute. Sounds good. Which means I think my radius calculation is too small. It's too small. And I think it's maybe this picture that's throwing me off. It looks kind of small if I'm looking at it. Whereas if I look at this picture, it looks big. And if I
Oh, I
look at
see
this
what you're
picture,
saying.
it looks real big. Like this is the landing bay, and these are people. These are people right there. People.
Can we
person.
see for the landing bay in your measurement picture, how many red sections is that?
That is okay. Let's move a red.
Like
Let's move
two,
the red here.
like
Let's move the
two.
red.
2.5.
Maybe 1, maybe
Oh.
2. Let's say 2.
Maybe 2.
A
So
little
if
bit
a
less
red
than-
section we said was
It was 3
2.6
floors.
meters
It
times
was
3.
Yeah. And that is 2.6 times 3, so that's roughly 8 meters.
Mm-hmm.
I think
24 feet, something like that.
yeah, this is more than 8
Oh,
meters.
that's way bigger than that. Yeah, that's way bigger.
right. So,
Okay, so-
I
so-
go ahead.
Sounds like that middle picture you have, the picture immediately to your right. Sounds
Yeah.
like maybe there's some distortion in the camera lens when this was taken.
Maybe.
Something like that.
Maybe I got there's 2 rows of windows plus 1 more. Maybe those rows of windows don't represent a floor, could represent multiple floors.
That's true.
That could throw it off.
I wonder
Maybe
if
this
this
is-
was to scale, would this ring be like out of the picture?
Maybe. Yeah, it like in order to get this particular shot, they had to compress the look.
Exactly.
And so that threw it off. Yeah. Okay. It was a fun calculation though. But I think
Yeah.
gotta pay attention to your scales, you know, when you do these kind of calculations. If you do these calculations all the time, which we do. So I think
Very cool.
probably they were shooting for something like 0.5 to 1. So in order to increase that to 1, we need to multiply this by 10. So we're looking
So you'd
at
have a much bigger ring. And that's also good because then you get more space available. I guess you just
Right.
have to have more mass to bring it up into space.
yeah. And actually, now that I think about it, if we want to get this to be 1G, so you got to multiply by 10, which means you're multiplying this roughly by 10, which is about 500 meters, which would mean the radius they designed this for was about 1 kilometer. Okay. Now we've got 1 revolution per minute and 1 kilometer. Those are pretty reasonable numbers. And then if you're on the inner part, you're not feeling the full G. It's only on the very outer edge you're feeling the full G.
Right.
So maybe in these compartments, you're sitting at like 1 G for 100 meters across. 1 kilometer diameter and 1 revolution per minute. That seems reasonable.
Sure.
Okay. So I think this number's off.
Yeah, reasonable. Yeah, so calculation, you had the correct equations, the theory, how to get there, but then in the measurement, which was challenging measurement, maybe there's iffiness there. But okay.
Yeah. Okay. All right.